Okay, can you all hear me? Yeah, probably. Okay, cool. So yeah, as Marco said, my name is Luka Jacobowitz, and this talk is titled "Oh, All the Things You'll Traverse," and it's about like traversals, I guess. Okay, so quick about me. I work at Codecentric in Düsseldorf for now, and I co-organize Scala Düsseldorf and Idris Düsseldorf meetups. So if you find yourself in Düsseldorf and you want to give a talk about Scala or something, talk to me. And I also maintain various CATS libraries as well as Outwatch, which is this other cool Scala.js thing. And I'm enthusiastic about FP, and that's exactly why I'm here. So today, on today's agenda, we have type classes, monoids, functors, and traversals. So this might sound a bit scary for some of you, maybe not. But a quick show of hands, if you have hands free. How many of you have used type classes before? Yeah? Okay, that's cool. How many of you have heard of type classes? Cool. Great. Excellent. So yeah, I'm going to go from 0 to 100. Okay, so type classes, what exactly are they? So we have this construct which was, as far as I know, developed originally for Haskell. And what type classes can give us is a different way to do polymorphism, right? So I think a lot of you, when you think about polymorphism, you think about subtype polymorphism. And type classes give us this thing called ad hoc polymorphism. And what that means is that we can define interfaces and then give instances of these interfaces to types that are already defined, so we don't have to do this up front. So I'll show you an example in a bit. And unlike standard interfaces, for example in Java or traits in Scala, these type classes, they don't operate on actual values or like instances of classes. They operate on types, and there are a lot more types than classes actually. So we'll see about that as well in a minute. Yeah, I already said that they're pretty similar to OOP interfaces or traits, and for now there's no explicit language support in Scala, but that might change in Scala 3 in about 2 years. We don't know yet. We'll see. Okay. So a very, very quick example, we have this thing called a show type class. And right here is how you would define it in Scala. This add type class annotation is an annotation by a small library called Simulacrum by Michael Pilquist. And it's basically just there to give Scala like native language support for this type class construct. And yeah, so what we have right here is this show type class, and it operates on this generic type T, and then it also has a method that that's called show that turns a value of type T into a string. So it's basically like an abstraction for the toString method that is commonly found. But unlike that, we don't have to define it when we create a class. We can actually define it after the fact, right? So for example, for things like string or integer, we can define type class instances, which are like the instantiation of an interface for these things, for things like string or int, which we would normally not be able to do if we were to just use standard trait, right? Because we can't say, hey, I want this thing string extends show. That doesn't work, right? So what we can do here is we can create implicit values for these type classes and for a specific type. So in the first example, we have here an instance for the show type class for the string type. And we can define it just by using this new show string and then defining the value here. And we see that that all occurrences of T are here replaced by string because we define it for a string. And the second one is for integer, for int, and it showcases that we can also do this with SAM types, right? So because this is a trait that has a single abstract method, we can also just declare it as a function, as an anonymous function. That's a feature that was introduced in Scala 2.12. And yeah, if we've defined this, now we can actually use it in our code. So for example, if we have this very, well, it's not a great method, but this very example kind of method, empty if false, and it works for any type T which has a show instance, right? And that's specified by this double colon and then the show type class name. So what this is actually called is a context bound, and it means that this method will only work if the type T you're calling it with actually has an instance of show in scope somewhere. Like, okay, and then we can see we can use this t.show, this .show syntax, and that's exactly what this add type class annotation gives us, is this syntax to just call these things inline. And yeah, that's a very basic example. Now let's look at something a bit more useful, right? So there's this thing called Monoid, and it is super, super cool, and it seems very basic at first, but we'll see why it's cool right now. So Monoid defines two methods. One is this empty, and it says that, hey, for any type T, this type T has to include some kind of empty value, right? So for example, for integers, that would be 0, or for strings, that would be the empty string, or for lists, that would be the empty list. And then it also needs to define a way to combine things, right? So if we here, this combine method has two parameters, a, b, and then it returns a new t at the end, right? So for example, for integers, we could use something like addition, right? So that is a way to combine two integers into one, or list concatenation, string concatenation, right? And this is exactly what we can do right here. We define instance of monoid for integer. And we say that, hey, empty is 0, and combine is just a plus b. And this is cool because if you think about it, like if you were to make Monoid a standard OOP trait instead of a type class, how would you define this empty thing? It doesn't really work because empty takes no input and it just gives you back a thing. So for every type T, it has to have an empty value. And if you wanted to do this with a standard Scala trait, it just kind of wouldn't work, right? So what can we do with this? So for example, probably a lot of you or some of you have written this thing. This is just a basic fold over a list that sums up a bunch of integers, right? So we have this list of integers, and then we fold left, and the first parameter in the first pair of parentheses is the seed value, and then we define a method, an anonymous function to accumulate the values inside. And see here we have 0 and plus, and we can do the same thing to sum strings, or to some sets, which have an empty set and the union as they're combined. And actually, like if you like see my point, this is actually, these are all instances of monoid, and we can actually do this very generically, right? We can sum anything where T has a monoid, right? So a list of T, we can create, we can accumulate any list of T's into a single T if T has a monoid instance. And that is exactly because we can call this, Monoid gives us this empty method and this combine method, right? So, and of course, this might look a bit weird because, hey, what's this kind of syntax? But that is exactly another thing that simulacrum gives us. And it says this, hey, if I have this type T, and because I have this context bound on T, which is monoid, then I can call an empty value for this T by using this monoid t.empty syntax. And then we can just call the combine method, and now we can call sum with whatever, and now we don't need to define all these methods. We can just say, hey, sum up whatever it is if it's a monoid. So that's cool. And another really cool thing about type class is that we can do this thing called implicit derivation, right? And what this thing does is, it looks a bit weird, but it's just pattern matches on things, and if both are sum, it will return the actually I just defined this inline, but this this pipe plus pipe is actually the monoid combine operator. So I just introduced this right here, and that is exactly equivalent. It's an alias for the combine function, right? And so the combine methods of two options is just if both are sum, combine their content, and if one of them is none, just return the one that is sum. If both are none, of course, you return none, because that's all you can do. And what we can do here is define a monoid for option if and only if the t inside that option is also a monoid. And that is actually one of the most powerful things, because if you think about it, we can define this for a lot of things, and we'll see about that later. And yeah, so implicit derivation is really, really cool. So type classes versus subtyping. Type classes gives us operations on types instead of values, right? So this is what we mean when we call empty on the type instead of a specific value, because we don't have a value, we just want to get one. And this comes in really handy when dealing with type classes like monoids, and there are a couple of others that are similar to it, and that's why type classes are really cool. Yeah, and we can derive instances for data types that might hold other data types. So we saw this with option of t, where option of t is a monoid only if t itself is a monoid, right? So if we have data types that hold other data types, then we can also create instances for these. Okay, does that make sense so far? Yeah? Okay, cool. Yeah, so what's really cool about monoids is that they're really, really everywhere. So for example, here we have monoid for a function. So if the return type of a function is a monoid, the function itself is also a monoid, and we can see this by looking at this definition. The empty method for a function is just returning the empty method of b, right? So this is just a constant function that will always return the empty method of b. And if we want to combine two functions that return b, where b is a monoid, then we can say, hey, just run both of these functions with a given a, and combine them. And then we get this whole new a to b function that will have combined these values. And we can do the same for tuple, right? So tuple is a monoid whenever a and b, so both sides of the tuples, are monoids, right? And that makes sense because we can just combine the individual values, and it all works out that way. Yeah, but this also works for tuple 3, tuple 4, and tuples of all RDDs. And it also works for either. It also works for maps, right? So for example, with maps, if you want to add two maps together, you look at the keys, and if you have a conflict, you just use the monoid combine operation to combine the values to get rid of the conflicts. And there's also future, right? So if you want to combine two futures, two future values, then you can combine them using the operation on A, right? So when we run two futures, and then at the end we just combine the results with the monoid combine operation. And there's many, many more. So this is just a small sample, but monoids are really, really everywhere. It's really cool. And so what we can do with this, so monoids applied, is we can write a thing that basically takes like a list, or actually not a list, but like a huge text file. And then what we can do is we can walk through it word by word, right? So what I do with here is this data actually just walks through the so this lines file is just a bunch of lines in a text file, and then we flat map it to split on every word. So up to the map, it's just a bunch of words, a list of words. And then we map it using the step function. And the step function returns a tuple of two integers and a map from a string to integer. And what it does is it says that, hey, for every word, it will return 1, then the length of the word, and then the map from that word to 1. And if we combine values of these tuples with 3 values, right? Because monoids with this tuple 3 value actually has a monoid instance. Then, for example, if we combine hello and world using this function, then we get 2, and then the combined values of their word lengths, right? And then a map from hello to 1 and world to 1. And what that means is basically, hey, we have a way to count words, we have a way to count characters, and we have a way to count occurrences of a word in the whole text file. And so what we can do is we define the empty method, the empty value of this monoid, which is just int map string integer. And then what we can do is fold over the whole thing and get back all of the number of words, the number of characters, and a map that contains all of the occurrences from each word to well, its number of occurrences. And well, this looks kind of cool, but we can actually make it even shorter. We can just say, hey, this whole fold left empty and then combine is just combine all, and now we don't need to actually call this empty method at all. We can just say, hey, combine all, and this is exactly what cats gives you. So this works in cats 100%. And yeah, in general, combine all can be seen as fold left with an empty seed and then using the monoid combine operator to get it all together. So this is pretty cool, I think. But we actually need to look at something called laws, and this is pretty pervasive in well, these cats type classes in general. But Monoid only has 3 laws, and they're very basic. So the first one is associativity. And I actually learned about this in like 6th grade, so it's really basic. It's nothing fancy. And associativity basically only means that if you combine x and 1 first and then combine it with z, it should be the same as combining y and z first and then combining x with that. So it basically means you can shift around the braces, and yeah, that's all it means. And it's really handy. We'll see about that. So it also means we also need this thing called right identity, and that means that if we combine something with the empty value, it should still be the same value, right? So if you combine 10 with 0, it should still be 10. And the same goes for left identity. And those are all the laws. And it might seem a bit insignificant, but I'm actually going to show you why these things are important. So you imagine you want to combine a list of, this is only 8 values, but it could be more. So we have these 8 values. Actually, it's just 7, I'm sorry. 7 values. And then, because we have these laws, we can actually transform this program into a different program that still obeys these laws. So what we could do with this, for example, because of associativity, is to say, hey, we want to group these into pairings of 2. And then, of course, we have this G, which doesn't have a pair because it's only 7 values. But we can, because of their right identity law, we can say, hey, this is actually equivalent to G plus empty. So why is this cool? If you think about it, because of associativity, if we have a very, very large list, we could actually do like folding, or this combine all, completely in parallel, because we have associativity. That means that this program is the same as the one above, and that means that, hey, we can do all of these individual steps, these individual pairs, we can compute them completely separately, and then just combine everything at the end. And that means that basically, hey, we can write a fully parallel version of fold. I think that's pretty cool. So how does it look? It's actually really simple. So for example, what we do is we have a list of some type A, which has to have a monoid, of course. And then we group it by, for example, the available processors. So if we have a 4-core, this list will now contain a list of lists that will each have 4 elements. And then what we can do is fold the inner values, the inner list that are all values of like 4. And then what we can do is say, hey, use this parallel map function that will map all of these things in parallel, and inside that, so it's just like map, just in parallel. And then inside there, we can just use this combine all function we saw earlier. And then at the end, we'll just call result. We'll just call combine all on that inner folded to get back an A. And now we've completely folded our data structure in parallel and got back an A. So an A could, of course, be everything. We've only seen like things like int or string or tuple so far, but at work we have like these giant data structures that we can actually define monoid instances for, and it's actually pretty simple. So yeah, that's that. So let's talk now about functors. So this is the functor type class, and it looks a bit more fancy, but it's actually just a generalization of the map function. So for example, you have list.map, vector.map, future.map, option map, and it's just a generalization of this. And unlike monoid or show that we saw earlier, it doesn't take a value of type T or A, but it actually takes like this thing F and then bracket underscore. And what that means is that it's basically what we call a higher kind of type. And that means in essence that we can, this isn't an actual type yet, it's what we call a type constructor, right? So F itself isn't a type, it's like option. Option isn't a type. Option is only type if you give it another type, right? So option of int is a type, but option itself is not. Option of string is a type. And it's the same thing here. F is not a type, but f string would be, and f of int would be. And this map function then just says, hey, if you give me an f of a and a function to turn all a's into b's, I can then give you an f of b. And of course, this works for things like list, option, either, vector, future, all of these things that you probably use every day, right? So that's cool, but let's talk about monoidal functors. And monoidal functors are really cool because they combine all the cool aspects of monoids with all the cool aspects of functors. And so, for example, we've seen this. This is a simple monoid. We use this combine function to combine two a's into a single a. And we can also do things with like higher kind of types. For example, option of a combined with an option of a is also an option of a. But what if we actually like had something like option of a and option of b? Like, how could we combine those? How does that work? So what could be the return type here? Maybe someone wants to take a guess. Like, what could we do with this? A to b. Yeah, well, yeah. So I'll just say it's a tuple, right? So if we can combine these in general for like an option, if we can combine two options and then use the monoid inside to combine the option, we could also create a tuple if and only if both are sums, right? And yeah, so this is the basic property of monoidal functors, but we'll look into this in a little more detail. And the monoidal type class defines two functions, and the first one is a lot like the combine on monoids. It's called product, and it takes an f of a and an f of b and gives us an f of a and b, an f of a tuple of a and b, right? So it combines two type constructors of f and then says, hey, I can give you both of these values. And because it extends functor, we can also then map over this to turn it, for example, into a f of c if we have a function from a to b, a and b to c, right? And then it also defines this pure function, which can lift basically any value into this monoidal context, right? So if you give it an a, it can give you back an f of a. And this one is pretty much an analog to the empty function on monoid, which we'll see about. So for example, I talked about option, and actually option has an instance for monoidal, and the same with future. And future, it's actually, this one is really cool because if you've ever wondered how to like run two futures in parallel, this is exactly the way to do it. Say like, if you have a future of like integer and a future of string, you say, hey, just use this product function, then it will actually run both in parallel and then return, once both are done, a tuple of integer and string. And yeah, what we can do with this is generalizing future.sequence. So how many of you know about future.traverse or future.sequence? Okay, only a few. Okay, well basically what it does is it has this type signature and it takes a list of futures and turns it into a future of list of something. And what that means is, in essence, so if I have a bunch of future values, I should run them all, and then when all of them are done, accumulate all of those values inside this list, right? And you can see that basically by the type, because that's almost the only thing it could do, right? List of future of A, turning it into future of list of A, that's basically the only thing it can do. And yeah, so maybe we can make this a bit more general. So we have this function list of future of A, and it returns future of list of A. And what we can then do is say, hey, we don't want this. We don't want this to be specialized to future. We should be able to use like a generic construct instead. And this generic construct is actually the monoidal. And this might look a bit crazy, but I'll try to go through it step by step. So we have this list of f of a. And then what we want to do with this list is we want to fold over it. And at the end, we want to get back an f of list of a. And to do that, right, we need to give it a seed. And the seed is just an empty list, right? And then we use that to lift it to f, right? So we have this list.empty, and we give it to monoidal.pure to get an f of list of a, which is also the result of our function. So that's the seed. Now we need to actually give it the combined function. And because the list has f of a's, the individual values coming out of this list will be values of f of a, which is this fa parameter. And then we want to accumulate these inside this f of list of a. So we have this function from f of a and f of list of a to f of list of a. And what we can then do is just say, hey, let's use this product function to create this, to combine these two f values into a single value, right? So now we have a value of f of a tuple of a in list a, and then because we can also map over it, we can say, hey, just add this a to the list of a's, and that's what this prod.map does. So it might look a bit scary, but it's actually not really scary. And yeah, what you can see here is that if you remember the combine all example, which was basically just like a fold left with monoids, it's actually really similar. We have this pure, monoidal pure, which is basically like the empty value of a monoid, and we have this product, which is like the combined value of monoid. So monoids and monoidal functors are inherently related, as you can see here. Right, and we can do the same for, So what we can actually do is say, hey, we want to, like, product and then map is so common that we can actually just have this thing called map n, which basically combines these two steps. And it says that, hey, if you want to combine, if you use product, fa and b, and then map, you can just have this as a shortcut, say, a tuple of fa and fb, and then map n f. And that is also available in cats, and it works pretty well. So we can also generalize future.traverse. And traverse looks like this. And basically, we give it a list of a's, and then a way to turn a's into future of b's. And if we were to just use map on this list with this function f, we would get a list of future b. And then we could just call sequence. So basically, traverse is like map and then sequence. It's kind of like how flat map is map and then flatten. So there's another parallel there. And it looks very similar. Right, we have, we fold right, we give it an empty list as the seed inside this f context, and then, but what we have instead is we have only values of a. But with the f function, we can turn them into f of b, and then we can just use this map n combinator again to turn it into an f of list of b. And yeah, that's future traverse. And yeah, as I said before, traverse is exactly equivalent to map and then sequence. So, and actually the cool thing about this is that the laws are exactly the same. So all of the laws for monoids also work for monoidal functors in that we have to have associativity, right identity, and left identity. And yeah. So actually I have a very small secret to tell you, and that's that what I called monoidal so far is actually usually called applicative in programmer circles. So like the category theorists that came up with this whole thing, they called it monoidal, but like Haskell and Scalzi and Katz, we call it applicative. And yeah, that has a bunch of reasons that I'm not going to go into, but I actually think that monoidal is a better way to get an intuition because it basically like lifts this monoid thing into the functor world. And, but yeah, from now on, I'm just going to use the term applicative so that when you actually like try out cats, you don't get confused. Okay, so Next up, we have this thing called a foldable type class. So, and in all of our examples so far, when we want to like fold over a list, we just use list. Or if we wanted to fold over a structure. But we can do the same for things like vector or stream. So we have this foldable type class, and it defines two methods. One is called foldMap, and the other is called combine_all. And we've seen combine_all before, and it says that, hey, if we have like a list of m's, we can fold them all together into an m. And this is actually a more specific version of foldMap that says that if I have a list or any container f of A, and I have a way of turning these A's into M's, which are monoids, then I can fold them all together, right? So it just takes out element one by one, transforms them into this M, and then at the end folds them all together. Yeah, and again, it uses this higher kind of type constructor to say that f is generic. So we could use these for list, for example, for vector, but also for things like option, right? So option can be seen as a list, for example, with only 1 or 0 elements. And that's actually really cool because we can say, hey, vector.combine_all, vector.foldMap, and we can call a lot of these things that we've learned, not just with list, but also with vector and stream and all the other collections. And we also have this thing called the traversable type class, and that's actually what gave this talk its title. And we have this type class called traverse, and it extends both foldable and functors. So what you can do, if you have a new collection, for example, or something similar, you can just define a traverse type class instance, and you also automatically get all this combine_all, foldMap, but also map for free. And it combines, and it uses, it defines these two functions, sequence and traverse, that are actually already in the standard library, but specialized to future. And what these things are, they work in general, right? So you can see here once again, instead of a list of f of a, we have this t of f of a, and we turn it in f of t of a instead of f of list of a, right? So this is very generic, like super generic and very abstract, but it's actually really useful because we have tons of different instances of traverse and also tons of different instances of applicative. And now we can just say, hey, define an applicative instance for this and a traverse instance for this, and now you can combine like n times m different things using this. And yeah, and what I like to like my intuition is that we can turn type constructors inside out, nested type constructors. So we have a t of f of a, and we turn it inside out into an f of t of a. And traverse, again, is just map and then calling sequence, right? So the sequence is actually the key to this type class. So yeah. And again, we can define this for vector, for option, but also for things that have multiple type parameters. So for example, either takes 2 type parameters. One is on the left side and one on the right side. But we can also define it for things like either where the left side is a string. And then we say, hey, if this thing has a left value, we won't traverse over it. So it treats it kind of like an option where the left side is irrelevant. And this might be a bit weird because we're basically fixing the left type to a string, but we can actually say this, hey, we want it for any type E by using this kind projector syntax, which adds this very convenient little question mark. And it basically says that, hey, I have this either thing, and I need it to be a type constructor that only takes a single type parameter, right? And so this thing is equivalent to things like option and vector that only take a single type parameter instead of 2, by basically saying this is the hole where it needs to go, right? So for example, we could say option and then in square brackets the question mark, and it would be equivalent. Okay, so that's that. Yeah, so what can we do with this? We can turn lists of futures into futures of lists. That's cool. We can also do something like this. We can turn stream of options into option of streams. We can turn either E or IO of A's into IO of either of E and A. right? And we can also do things like vector validated NEL, error or A into a validated NEL. What? So what the hell is validated NEL? Okay, validated NEL is actually a really cool thing, and I'll explain it in detail. So we have this thing called validated, which is a sealed trait, so it's an ADT. It has two type parameters. One is like for the invalid types and for the valid types. So the first case of this is the valid, which just has a single value of A, which is the valid type. And then we also have a constructor that represents the invalid values. So, and that's basically all it is. So what we have is something that is actually like very similar to either, but has a different naming. And so it's either a value of type E or a value of type A. And what can we do with it? We'll see. So we also have this validated NEL, and validated NEL just stands for validated, where the left side is actually a non-empty list of E and A. And that means that basically, well, non-empty list is just a list that is guaranteed to have at least one element. And yeah, so we can define validation logic using this type validated. And what we do, for example, if we want to parse a string into something like a user type, then we can use this validated type to say that, hey, this might return either a non-empty list of errors, or it might return a valid user. So this is basically how a lot of functional programmers like to do validation. And then, if we have something like a bunch of a text file again, lines, we can traverse all of these using this validate function and turn that into a validated NEL of error or a list of user. And so that means that, hey, we had a list of strings, and then we traversed it to get either a non-empty list of errors or a valid list of users. So we can basically do like full text validation with this very, very small single implementation. And that's really cool. Yeah. So, still not convinced, maybe? What I did was I went to Stack Overflow and looked at the last 6 months, and there was a very, very common theme among questions I answered. And that theme is traverse. So, if I have this weird construct of list of either t future a b, and I want to turn it into either t of future of a of list, hey, that's like turning this list inside out, right? So this is the answer to this is just traverse. How do I transform a list of IOs into an IO list? That's traverse. How do I turn either of error of option of either, oh my god, to either of, oh, okay, that's traverse. List of Kleise to Kleise list traversed. Combine valid values of seek validated, and I was like, oh, what's this? And then inside the question he says, hey, I have this seek of validated non-empty list, my string, and I want to turn it into a validated non-empty list of seek, and that's exactly what we just had. And that's, of course, just traverse. And I had this guy recently that said, hey, I have this thing, I want to do this cool stuff with it, I have a validated NEL, and I want to do this user thing. It's like, he created this 5 or 7 line implementation with like really long stuff, and it's actually just validate registration, traverse, add users. So traverse is really, really generic and really general, and you can use it almost everywhere, and it's super cool. And yeah, I have a small bonus slides. So what we've seen so far was monoids and monoidals, but there's also a notion of semigroups, and semigroups look like this. So they're exactly like monoids, but they don't define the empty method. So they only have like an associative combine method. So they're basically just describe associative binary operations. And then actually in cats, monoid actually extends semigroup. So every monoid is also a semigroup. Yeah, and what can we do with semigroups? Why are they useful? So for example, who has dealt with this? So Java lang unsupported operation empty.max. No one? No one dealt with that? Okay, well, it happened to me a lot of times. So whenever you have an empty list, and you of course, you don't know at like runtime that your list is empty, and you call this max function that is defined on it, then if it is empty, we'll just throw an exception at runtime. That's almost never what we want, right? We want all of our logic to give us errors at compile time and not at runtime. And of course, the same goes for things like reduce. So if we have a list that is empty and we're going to call reduce on it, it can't do it because it doesn't have an element to fall back to. Yeah, and this is the same runtime exception in essence. And of course, we want to do the same thing with this non-empty list that I introduced earlier. Non-empty list actually, well, by default, by design, it's not able to be empty. Of course, that's where its name comes from. So if you say non-empty list, open bracket, close bracket, then it says, hey, dude, you got to give me at least one argument, right? So at least one A. And yeah, of course, now if we use non-empty list and use this maximum function that's defined on it, this is completely safe. And this one will never, ever throw at runtime. And the same goes with reduce. Reduce is completely safe on non-empty lists. And this is because non-empty list is a semigroup. And yeah, that's exactly why they're cool. Another thing is that we have this thing called Semigroupal Functors, which are exactly like monoidal functors or applicative functors, but they lack the pure function, right? So this is just a thing that extends functor and has this product function. And then monoidal just extends semigroupal. And of course, because these are not its real names, these are actually apply and applicative. And what we can do is that if we have a non-empty list, for example, we always use this applicative to traverse over things. But sometimes we can't define an applicative. We can only define an apply. And if we want to traverse over that, we can only do it if there's if we have a non-empty structure, right? And this one example of a type that doesn't have an applicative instance but has an apply instance is the very standard map, right? So if we look at an applicative for map, we need this pure function, and the pure function says that, hey, I give you a value and you give me a map of keys and values, but that actually doesn't work, right? Because whenever we want to insert something into a map, we need it to give us, we need to have both a key and a value. We need a key value pair. So if we give it just a value of type V, this whole thing doesn't work, right? So we can define a product function, but we can't define this pure function, whereas with apply, which is the semigroupal version, we can do this very easily. And then we can use non-empty lists, for example, to traverse over, over this map. And that's exactly what we can do. And yeah, I think that's it for me. I have a small conclusion. So we learned about monoids, functors, applicative functors, and foldables. And we also learned about some of these other things CATS gives us. Those are non-empty lists and validated. And of course, we also learned about the almighty power of traverse. And yeah, I hope that at least some of you actually take with you that this traverse function, you need to use it everywhere, because like all of your code is actually like a specialized version of traverse. I'm just kidding, but yeah, a lot of code can be saved by using this traverse function. And yeah, I hope this was a very good like gateway drug thing to the CATS library. I hope you all start to use it. And yeah, are there any questions? And thank you for listening.
Thank you very much, Luka. All of this stuff is stuff that we're actually using every day. Traverse, sequence, that sort of thing. It's actually really cool and helps us save lots and lots of money on avoiding carpal tunnel syndrome and that sort of thing. So that's really cool. Let's do questions for Luka.
So this is not directly about Traversable, but it's more about CATS. So sure. You said that Scala, the language, can't actually do this stuff, but CATS can. You said, sorry, support for this is not in Scala until Scala 3, maybe.
Yeah.
So does CATS implement this with like macros or other metaprogramming techniques, or how does it work?
Right. So exactly. And what we saw earlier is this at type class annotation. That's basically a macro annotation that will generate a bunch of boilerplate. So how it works is it just uses like implicit dictionaries. So what you have is this, if you define something like this applicative, it's just an implicit value. And then at runtime, at compile time, when you have a function that uses this context-bound syntax, right, with a double colon, it's actually just syntactic sugar to say, hey, I need an implicit value of applicative for this f type. And that, in essence, means that it just works with implicit. So that part is actually really simple. And the only thing Simulacrum is doing is giving us a bunch of syntax. So we want to be able to call list.traverse, whatever. And without Simulacrum, we would have to say, hey, give me this type class implicitly, and then say traverse, and then give it the list and the function. And so basically, yeah, the Simulacrum library in Cats, we try to make it as easy as possible. But none of this is actually like magic or anything. So I think it's actually really simple, and it makes a lot of sense. Yeah, I hope that answered your question. Okay, cool. Any other questions?
All right, cool. So I'm going to plug something as well. Tomorrow we have Scala Bridge here at Klarna, and we're doing 2 tracks this time around. So one really like beginner basic track for getting into Scala and functional programming, and then we're also doing a track that essentially has you using all of this cool stuff. So if you're interested in doing that, just hit us up on the Slack channel, the Scala channel, or go to Bridge Troll and sign up for the event. And it's free. Klarna's paying for everything. There'll be food and booze. So what's not to like? Thank you all.